The HiFi amp project that we're doing, and this is a schematic of the monaural one. So it's the same circuit, just twice, but it's on the picture. And so let me explain what circuitry is there. It's like the talk I gave on the champ a few weeks ago. This yellow block in here is actually an op amp, and the first stage right here is a common cathode amplifier, just like the champ. And then it feeds into what's called a phase splitter, which is a triode also, that creates a gain of 1 and -1. So you just get the opposite sign of it. And then that's driving a power pinto tube, just like in the champ. But what you're getting is one's going up and one's going down. They call this a push-pull amplifier. And what you're going to get is double the voltage. So that gives you 4 times the power. This tube that they're using isn't as big as the one in the champ, so this is an 8-watt amplifier. But the design in the champ, when you take it and do the same thing, you have to tweak. That's like a 22-watt amplifier. So we're building some of those also. And the power supply for this is a little different. They're using a semiconductor diode bridge, and what this is going to give you is a very nice folding over of the sine wave that's coming in here. It's creating a couple hundred volts to run the tube, and then running it through 2 RC filters to smooth it out as much as possible. With the champ, the diodes were vacuum tubes, but they have a response time. So when you draw a lot of current, the voltage dips, and then it'll come back again a few milliseconds later. So you get a sound effect from it. Now when you're playing some hi-fi stuff, you really don't want to do that. So they added this in here. What that's going to do is actually lower the distortion. I was going to show that in some of the video clip that I was doing with this. And then there's a volume control here, and just a capacitor to block any DC. And then what we do with the mono block is take the right and left channel and add them together, and just have one speaker going out. With the stereo, one goes to the second amplifier and one to the first. But this configuration's got a resistor on the back. That's this over here. And another resistor here, and roughly the gain is 1 plus the resistor ratio if this gain is really large. But because there's really only one tube that's amplifying, and this is giving me a gain of 1 in opposite phase, and then another gain of 1, it's not a lot of gain, but the feedback reduces distortion. So the overall gain, if you take 1 plus this resistor ratio, would be around 40 or 50, but I'm measuring gain around 20 or 25. And the reason is that there's not that much gain in this amplifier. So that's roughly how the thing works. I added this safety plug in a grounded system, so I've got it in a metal case. I've got a plate underneath it so that you can't stick your hands in there and get electrocuted. The kit comes with just a wooden block, and you just got to touch it and you're dead. So if you got a little brother or sister, say, hey, what's this? And they're gone. So I wanted a box. I wanted the thing locked, so you really have to unscrew it to get inside of it. And then you're on your own. So that's what's going on with this one. Again, very similar to the champ. Really, it's just creating a kind of a mirror image kind of thing and flipping it over, and that's how they're getting this this doubling in voltage. When one's going up, one's going down, the difference is double. Then I was trying to show, Peter had built this, and I work with each student. I just show them after we get the amp in the lab what tests I was doing on it, but I can't show all the equipment because it's actually at home. So while this thing is scrolling back, I'll tell you what's coming with this. So here's Peter's amplifier, and I'm hooking up the left channel and feeding it. Actually, the output of this analyzer is coming to this input. It's called the output over here, and then the input's on this side, which is the output of the amplifier. It's a little confusing when you see it, but this number over here is the frequency that it's initially testing at, which is 1 kilohertz, and I'm adjusting the gain to get 1 volt RMS out. And so on the scope, eventually you'll see here they've got a signal, and I'll eventually zoom enough on this to be able to see it. But it's 2.8 volts peak to peak. And so what it's going to do is make the gain at that value equal to 1. So it's actually going to make the input vary that so that the overall gain is 1. And it's going to start to graph the gain versus frequency once I click on this little OK button. And then that's coming up shortly after that. Then you'll see that the frequencies here start from about 20 hertz, and I clicked on it, I had to go get the camera back here, so it's about up to 30 hertz by the time I clicked it in there. And then over here, what it's giving me is actually the gain in dB. Initially just voltage, but you can't really see the little light that's over here. But it's going to go from 20 hertz to 100 kilohertz, and do 30 points for every factor of 10. Set the scope, so you saw a 1 kilohertz wave, and then when you go much lower in frequency, you're just seeing a part of that sine wave. What I'm watching for here, because this instrument doesn't have a scope face to it, is that the waveform doesn't distort. If it distorts, I'm really measuring its linear behavior, and it really wouldn't be an accurate representation of frequency response. So it's going to do this for each channel, and then it's going to get graphed. All this equipment is on a bus. There's quite a bit of software for these instruments. They all have the HPIV bus stuff on it, and there's people that have written software actually for free. This is a ham radio guy. He's got a ton of stuff on his webpage. And it's starting to graph the voltage gain versus frequency. And when it gets to 1 kilohertz, which is right here, the gain will be 0 dB, which is a gain of 1. But actually, if I were to turn the volume control all the way up and measure output over input, the gain's around 26 or 21 or 22, which is about 26 dB. On the minimum end of it, it's actually about a gain of 2. So come back here on the scope, and I'm now around 1 kilohertz, a little bit above it on 1.5 kilohertz. You can see that the waveform is nice, still a sine wave. And now as the frequency goes up, this will start to squeeze together as the frequency is going up. But one of the problems I have with the amplifier is that all of these now have a stability problem at about 100 kilohertz. So everyone that's been built, when I'm listening to them, I can hear a really high pitch in the speaker. And then I put it on the scope to see what was there, and I saw that it was oscillating. And then I looked at the feedback path, that resistor that came back around. They actually have a small capacitor across it. I did some calculations on the oscillation frequency and realized that capacitor is a little bit too small. So I increased the value of it, and that got rid of the oscillations. It really reduced the gain. What you'll see when it pans over to the graph is that when you get around 50 kilohertz, 60 kilohertz, the gain of the amplifier starts to go up. And when the gain, without that capacitor, this goes shooting up way up here, and any noise at that frequency sees a huge gain. And it just appears as a sine wave on top of your output. And so this is, I think, the left channel that's being plotted. But with that capacitor, I was able to push this down. Actually, it's below a gain of 1. Well, I should say normalized gain of 1. But it was much, much higher. In fact, it just shot way up in here, 20, 30, 40, 50 dB. So it's very common with amplifiers with feedback paths to actually have them go unstable on you. And so we fixed that out. I'm actually using some of the ideas in ECD 402 if you ever get interested in taking that class. And then I swept out the second channel to see how close they were, because of course you want them to be quite closely matched. So what's going to happen next here is it's going to plot this again versus frequency, and we'll see that the two channels are fairly close to each other. I've had some trouble with the pots that they give for the volume control. They're sometimes not that well matched, and I've had some very far apart actually, factor of maybe 5 or 6 dB apart, which is about a factor of 2 in gain, so it sounds weird. But those things you can improve on the design. You can spend a little more money and buy a little higher quality pot. This one's actually pretty well matched and sounds okay. But with anything like that, if you invest a little more money. I may replace those over time. I've had some fail on me, and so this one actually works quite well, but I've had a few of them go past the stops and they don't work. But here comes the second channel, and you can see that up here again, I've been able to push that down versus frequency. So that's one of the tests I look for. And actually, almost every amp has this kind of a problem at high frequencies, so you got to make sure you take care of that. Although you can't barely hear those tones, you are dumping power into the tubes and the transformers, the big transformer supplying it, so it gets pretty hot. Of course, your speaker's actually getting those voltages too, so you're dumping power into that too.